You know those gray metal boxes you see everywhere, humming away on utility poles or sitting inside those fenced-off neighborhood substations? They might not look like much, but honestly, they are the silent, unsung heroes that make our entire modern world tick. Let's really dig into what they're all about.
So, it all boils down to one massive problem, right? How in the world do you get huge amounts of electricity from a power plant, maybe hundreds of miles away, and then turn it into something safe enough to plug your phone into without, completely frying it? Well, the solution to that puzzle is a brilliant and, honestly, a surprisingly simple device. In this explainer, we're going to pull back the curtain on the machine that manages electricity's incredible journey. We're talking about the transformer.
So what is this thing? A transformer is a static device, and that's super important. It means it has zero moving parts, which is the key to why it's so incredibly reliable. Its whole job is to take alternating current, that's AC, and change its voltage, either bumping it up or bringing it down, all without the two circuits ever even touching.
It sounds a little like magic, I know, but it's pure physics. And to really get how it works, we've got to look inside. A transformer, when you get right down to it, is really just made of three essential parts, all working together in perfect harmony. So first up, you've got the primary winding. Think of this as the indoor, the coil where the electricity comes in. Then you have the magnetic core, which acts like a pathway for an invisible force. And third, there's the secondary winding, a totally separate coil that acts as the outdoor, where the new, transformed electricity leaves. Now the secret sauce that links these parts together isn't a wire. It's a fundamental law of physics called mutual induction. And this is where the real genius of the transformer is. This whole idea actually goes way back to a scientist named Michael Faraday, all the way back in 1831. He's the one who figured out that a changing magnetic field could literally create, or induce, an electrical current in a nearby wire. I mean, that one discovery is the foundation for pretty much everything. Transformers, electric motors, you name it. So here's how it plays out, step by step. First, that alternating current flowing into the primary winding is constantly flipping direction, back and forth, back and forth. This creates a magnetic field around it that's also constantly growing, shrinking, and pulsing. This is the critical first step that kicks the whole thing off.
Now, this is where the core comes in. That soft iron core acts like a magnetic superhighway. Its job is to grab nearly all of that pulsing magnetic field and guide it perfectly over to the secondary winding, losing almost nothing along the way.
And finally, that moving magnetic field washes over the secondary winding. And just like Faraday discovered, this invisible moving field induces a brand new alternating current in that second coil. And just like that, power has been transferred right through thin air. No wires connecting the two. It's just brilliant. Okay, so transferring power through an invisible field is already pretty cool. But the transformer has another incredible trick up its sleeve: changing the voltage. And the secret to doing that is so elegantly simple. It all comes down to how many times you wrap the wire around the core.
It works like this. If the secondary coil has more turns of wire than the primary one, you've got yourself a step-up transformer, and the voltage goes way up. But if it has fewer turns of wire, it's a step-down transformer, and the voltage drops. The ratio of the turns directly, perfectly sets the ratio of the voltage change. So simple.
All right, now let's zoom out and put all the pieces together. Let's see how these two types of transformers work together in a huge, coordinated dance to power our entire world, from the power plant all the way to the plug in your wall. So it all starts at the power plant, where these giant step-up transformers boost the voltage up to super high levels for efficient travel. Then that electricity just zips across the country on transmission lines. When it gets to your area, a big step-down transformer at a local substation lowers the voltage for your town. And finally, that little transformer on your street corner steps it down one last time to deliver safe, usable voltage right into your home. Okay, but as amazing and as close to perfect as they are, transformers aren't magic. They still have to obey the laws of physics, which means that a tiny little bit of energy is always going to be lost in the process. But here's the absolutely incredible part. We're talking about a tiny amount of loss. A typical power transformer is somewhere between 95 and 98% efficient. That makes it one of the most efficient machines humankind has ever invented. So yeah, the losses are real, but they are incredibly small. So where do these tiny losses come from? Well, mainly two places. First, in the iron core itself. That rapid-fire switching of the magnetic field creates a little bit of heat, kind of like magnetic friction. And second, even the best copper wire has some natural resistance, and that also generates a small amount of heat as electricity flows. We call these core losses and copper losses.
So the next time you walk past one of those humming gray boxes, maybe just give it a little nod. It's a direct connection to a 19th century discovery that quietly and efficiently powers basically every single aspect of your life. It really makes you stop and wonder, without this simple, brilliant invention, what would our plugged-in, always-on world even look like?